Today, I am presenting a poster on magnetic microcalorimeters for decay energy spectroscopy. This work is a joint collaboration between the University of Michigan, the University of New Mexico, and Lawrence Livermore National Laboratory. Decay energy spectroscopy, also known as Q spectroscopy, is a technique of embedding radioactive sources within a detector itself. This way, the entire decay energy is measured within a single peak. Conversely, with modern semiconductor detectors, several peaks and several tails are typically observed in a decay spectrum. Magnetic microcalorimeters are cryogenic detectors comprised of a gold absorber, a magnetic sensor, which is a magnetic coil in a spin state, a heat bath, and a superconducting interference device to read out changes in the coil. In the cartoon on the left, a radioactive nucleus decays via alpha decay. This injects heat into the system, causing the temperature to raise. This changes the spin state within the coil and thus the magnetic flux. The change in magnetic flux is recorded by the squid and converted into a readable voltage signal. The system is then cooled back down by a thermal connection to the heat bath. Below it are two pictures, one of a gold detector and a second of a sapphire detector. The sapphire detector is a crystal with a gold pad embedded on the surface. It works in a similar method to the gold absorber described. The goals of this project are high resolution and high speed detectors, which will offer a new avenue for high accuracy radioactive material analysis, applicable in nuclear safeguards and nuclear forensics. Even though we are working to improve speed of detectors, the rise time is still in order of milliseconds. We have modeled the pileup for these detectors and are working on designs that allow a trade-off between response speed and response resolution. For example, uranium analysis, the decay energies of different isotopes are far apart, and so speed is preferred over resolution. Whereas with plutonium, the decay energies are very close together. Plutonium-239 and plutonium-240 have decay energies which only vary by 11 keV within the resolution of modern detectors. So here, high precision is required at the expense of speed. We are also working to study the effect of beta pileup. Beta pileup is a problem, especially the low energy beta from plutonium-241, because this can seep into the peaks and cause them to merge together. The pileup simulations have demonstrated that fast detector response times, or a fast rise time, are greatly advantageous over a slow detector response time. We have also performed initial measurements, a curium-244 analysis with not a decay spectroscopy, but the source external to the detector. We observed the alpha peak at 5.8 MeV, the plutonium-240 nuclear recoils, and the plutonium L-shell X-rays. We have also embedded americium-241, and the Q spectroscopy signal is shown to be dependent on temperature and thus detector design, as the temperature can be adjusted with thermal connections to the heat bath. We are currently planning experiments with realistic plutonium and uranium samples. We hope to improve the resolution by a factor of 10. Currently, we have a 0.2% resolution comparable to semiconductor detectors, but this is to be improved. The ultimate goal is a MMC-based spectroscopy system, which can be adopted by IAEA laboratories. Thank you very much.